feel free to get up and get drinks, snacks, whatever you want. But we're going to continue on into chapter 20, which is talking about amines. So we've already talked a little bit about how we can make amines, right? We've talked about the Gabriel synthesis. What's the Gabriel synthesis good for? Primary amines. It's very selective for making primary amines. How else can we make primary amines? Other than what's shown up there? Reduction of what?
Primary amide?
We can reduce a primary amide. What reagent would we use to do that? We can use lithium aluminum hydride, or we can use borane. Remember, we can use either one of those. All right. Now, somebody said something about cyanide. What can we do with cyanide to get a primary amine?
Yeah, cyanide and lithium aluminum hydride.
Yeah, so we use sodium cyanide to displace an alkyl halide, right? And we get a new carbon-carbon bond, and then we can reduce that nitrile with lithium aluminum hydride to give us a primary amine. We can also reduce what other functional groups to get amines? Okay, nitriles, nitro groups. What reagents would we use to reduce a nitro group? Technically, LAH kind of would work, but it's not the common one. What? Yeah, so reducing metal reductions using iron or tin and under acidic conditions. And what else? Hydrogen and palladium will also work. Okay. It also turns out you can make amines from azides. So you can take sodium azide, displace an alkyl halide, and then reduce the azide with a variety of reagents and get a primary amine. But the classic example is the Gabriel synthesis. Another way in which you can get amines, you can actually take carbonyl compounds, either aldehydes or ketones, and you can react it with ammonia, and you can get an imine. Where else have we learned about imines before? Pardon? Was it in that chapter? It was pretty close to that, yeah. So primary amines plus ketones and aldehydes give imines. Well, in this case, we're not using a primary amine, we're just using good old-fashioned ammonia. The reaction's the same. You get an imine intermediate, and then we can reduce that imine to get a primary amine in this case, okay? Now, if we actually started with a primary amine, we would get an imine that could be reduced into a secondary amine, okay? So we can do both, okay? So the trick here isn't the first step, because you already know that. You know that a carbonyl plus some type of ammonia derivative or a primary amine will give an imine. And now all we got to do is add hydrogen across that carbon-nitrogen double bond to do that. Many reagents will do that reduction step, but there is one reagent in particular that you need to have committed to memory, okay? And that is sodium cyanoborohydride, okay? The nice thing about sodium cyanoborohydride is it's pretty selective for the reduction of imines. So you can actually take sodium cyanoborohydride in the presence of the ammonia and the carbonyl all in one pot. You don't have to isolate the imine intermediate, because sodium cyanoborohydride only reduces carbonyl groups slowly, but it reduces the imine much faster. So it's a rate kind of reaction. Okay? These reactions are typically done in aqueous solution or alcohol solution. And so one of the hydrogens comes from the sodium cyanoborohydride. The other hydrogen comes from water. Okay? So here's a practical example on the bottom. This is how they make amphetamine. Okay? You take phenylacetone, which is shown there on the left, which is just a ketone. You take ammonia and sodium cyanoborohydride, and you can make amphetamine. This is not methamphetamine. It's just amphetamine. But if you were to make methamphetamine, what amine would you use to do that?
Methylamine?
Mm-hmm. So if you ever watched Breaking Bad, that was what they were always trying to steal, was methylamine, right? Because that's exactly the reaction they were trying to do. Okay? But you would hope that they wouldn't use sodium cyanoborohydride. Can anybody tell me why? You wouldn't have too many repeat customers, that's for sure. Okay? Huh? Why? They don't want to kill people. So, sodium cyanoborohydride is the reagent of choice, at least on a laboratory scale, because of its selectivity. Okay, you can take the ketone, the ammonia, which is usually as ammonium hydroxide, which, as you know, is an oxymoron. There is no such thing as ammonium hydroxide, it's just ammonia and water. And then sodium cyanoborohydride, you can mix all those together, and you can make your new carbon-nitrogen bond and reduce it all in one pot. And so it's a pretty nice set of reactions to do all in one step.
Does it have to be ammonia, or could it be
Any primary amine will do it. Okay, but in this particular case, since we're making a primary amine, you would start with ammonia. Okay, and so like if you started with methylamine, you would actually get methamphetamine in that reaction. Okay, so it actually turns out that sophomore organic chemistry is all you need to have to be a drug lord. Let's go. Okay. Well, but seriously, what's the limiting factor?
Get the ingredients, because the government has this stuff on lockdown.
Sort of locked down. So, for example, that simple little ketone that's over there, right? I have to fill out paperwork to purchase it. Hmm? That's not Sudafed. Sudafed is an alcohol. Yeah, you can take. Yep, pseudoephedrine. Yep, and that gets reduced to methamphetamine as well. But this is actually the mechanism, or the overall mechanism, that Heisenberg on Breaking Bad was using.
Is it not just, like, so the first ketone, can you not just make that quick?
You can, and that's what he did. But the ketone is actually controlled, and so they have to know that it's going to a legitimate use. You can't just go down to the hardware store and buy it. I can go to the hardware store and buy ammonia. It's called drain cleaner. I mean, you can buy that. But, and I also can't readily buy sodium cyanoborohydride, right? So
you wouldn't want to use that anyway.
If you're really good at what you do. Depending on what you, huh? It's a reduction, yeah. Mm-hmm.
He's like taking notes over there.
I'm not telling you anything that's not already on the internet. I mean, you can look it up. I mean, it's not a secret. That's it. That's all you got to do. Remove one functional group. So you would do a retrosynthetic analysis by simply looking at the carbon-nitrogen bond, recognizing that this is what you need to make. This part would come from the carbonyl, in this case an aldehyde, and your NH2 ultimately comes from the nitrogen nucleophile, which is the ammonia in this particular case. Mix the two together, form the imine intermediate, and reduce it with sodium cyanoborohydride. Okay. We also know that amines can react as bases, right? They're not only nucleophiles, but they also function as bases. And so some examples of the reactions are shown there. Equilibria favors the products. Can you tell me why? pKa, that's right. So we're going from a pKa of the acid, which in the top example is -7, and we're going to a pKa of almost 11, right? And equilibrium always favors the weaker pKa side, right? So in an acid-base reaction like this. So we're going from a much stronger acid to a much weaker acid in this process. Okay, and so we can take primary amines, secondary amines, tertiary amines. They will react with um, you know, the typical acids that we deal with, either carboxylic acids or mineral acids, as we like to call them, and give us the ammonium salts. And so in the top example, we're getting the ammonium chloride. In the bottom example, we're getting the ammonium acetate salt out of these. And so your pKa range for these protonated amines is going to be somewhere around 11-ish. Okay? Now we can use this to our advantage. So let's suppose you have a sample that contains an amine that you want to isolate from the remaining sample. So maybe that remaining sample is a hydrocarbon or a hydrocarbon and an alcohol. We can use the basicity of the amine to our advantage. So we know that amines and alcohols in this case, so I gave Gabby a mixture of the amine and the alcohol, and they both will dissolve in methylene chloride because they're both organic, right? And what she will do then is then she'll add a dilute solution of hydrochloric acid. Usually we just use a 10% solution. And so if we typically, let's say we start with, I don't know, 10 milliliters of methylene chloride, we would add an equal volume of 10% HCl. And we know that hydrochloric acid in water is not miscible with methylene chloride, and we know that the methylene chloride layer has to be on the bottom. How do we know that? Why does that have to be the case? It's density, right? We know that methylene chloride is more dense, so it's the bottom layer. Now, when she takes that separatory funnel, puts a stopper in it, and shakes it, a reaction will take place between the acid and the base. And the amine is the base, and so what happens is we get a protonated ammonium salt. What happens to that? If we make, pardon? It's a salt, and salts are more soluble in water. That's right. And so now in the water layer, we'll have the ammonium chloride salt of that organic amine in the water layer, and the alcohol, since it's dilute acid, it's not going to react. To react an alcohol and make an alkyl halide, we need concentrated hydrochloric acid, which we don't have here. It's pretty dilute. And so the alcohol will remain in the organic layer. We can easily separate these layers now, right? The bottom layer gets drained off, and it contains the alcohol. And the upper layer then can be drained off, and it contains the ammonium chloride. Okay? So how does Gabby get the free amine back? It's as the ammonium chloride now, but she wants the free amine. How are we going to get that back? So the water layer right now is acidic, and it contains the ammonium chloride. How are we going to get the amine back? Well, I've got 10 or 20 milliliters of water. That's way too much water. Drying agents are only good at removing trace water, right? So how do we get the amine back? Add base. And what base would I add?
Sodium hydroxide.
I would add sodium hydroxide. And in fact, what we do is we just simply add sodium hydroxide pellets until the amine separates out of the water layer. Okay, and if we're lucky, we can just filter it off. In this case, we would probably have to extract it back into methylene chloride and isolate it. Okay? So we can use the acid-base chemistry to our advantage. And if you end up ever working for somebody who does natural products chemistry, where they go diving off Hawaii and collecting things and having fun and then coming back to the lab and working for a year, this is the kind of stuff that they do. They will take a sample of whatever material, and they'll want to separate the basic components, the amines, from the acidic components, and they do these types of extractions for days on end until they finally get a fraction that has the properties that they're looking for. Okay, so we can use acid-base chemistry to our advantage to separate amines from other materials pretty easily. Okay, and so you all probably learned in Gen Chem about pKb. I think it's kind of an archaic term to think about. I always like to think about things in terms of pKa. And so if we have two amines and we want to know which one is the stronger base, we look at the pKa's, okay? And so which one of those would be the stronger base, ammonia or ethylamine? And why? And why? And why? What makes it more basic? The alkyl groups are electron donating groups, right? Absolutely. Whereas the ammonia does not have an alkyl group on it, right? So the primary amine is going to be a stronger base just simply by looking at the pKa's, because we know that the higher pK belongs to the weaker acid, which means that the conjugate base of that acid must be the stronger base, right? So I always like to just look at pKa values and forget about pKb. I think we still largely teach you all pKb just to drive you crazy. When pKa will answer just about anything you want. So for example, if we look at pyrrole and pyridine, pyrrole is actually not basic, hardly basic at all. Whereas pyridine is actually a fairly decent base. So we take pyridine, we put a proton on it, we look up its pKa value in a table, and we find that it has a pKa of 5.3. You take pyrrole, you put a proton on it, you look up the pKa for the protonated pyrrole, and you'll recognize that it has a pKa of 0. Okay? So what can you tell me about pyrrole? Obviously it's a weaker base, but why is it so much of a weaker base than pyridine? I mean, pKa of 0 is for kind of a strong acid, right? The protonated pyrrole is actually a strong acid, whereas the protonated version of pyridine, that's not a strong acid, 5.3. It's acidic, but it's not a strong acid. It does, and what does it have to do with that? Aromaticity. So, pyrrole without a proton on it is aromatic, non-aromatic, or anti-aromatic? Sam? Pyrrole without a proton on it is aromatic, anti-aromatic, or non-aromatic? Without a proton. Are you sure? Count the electrons for me. It's aromatic, right? But if it picks up a proton, those electrons are no longer in the ring, right? And so it becomes non-aromatic. Is that a stabilizing effect or a destabilizing effect? That's right. So to put a proton on it would destabilize it overall. So it's not a very good base. It doesn't want to do that to kind of give it human characteristic here, right? But pyridine, why will it readily accept a proton? Yeah, you're on the right track. So, pardon? Well, it's not axial. I know what you're trying to say. It's perpendicular, right? So the electron pair is perpendicular to the pi system, right, at 90 degrees. And so that lone pair is not counted in the aromatic ring. And when we put a proton on it, the pyridinium ion that we have on the left is still aromatic. Okay, so those electrons can function as a base. Doesn't disrupt the aromaticity of the pyridine ring. Whereas if I put a proton on pyrrole, I'm going to disrupt the aromaticity of the pyrrole ring. And so that's why pyridine is a much better base than is pyrrole. Okay? Other reactions that we can do with amines, we've talked about amines as nucleophiles. We've talked about amines as bases. But amines can also function as potential leaving groups if you modify them. The NH2 minus is not a good leaving group. Okay, I cannot treat this with a base by itself, have the base come in, abstract this proton, and these electrons kick out NH2 as a leaving group. Okay? Now I said that, and it just came to my mind that there are a few exceptions to that rule. But for all practical purposes in this class, the answer to that is no. But what we can do is we can do what's known as the Hofmann elimination reaction, where we take the primary amine and react it with an excess of iodomethane. And then we treat it with silver oxide, and then we heat it up. And what happens when you do that is you get an elimination of, essentially, what are we eliminating? What elements are we essentially eliminating from that amine? We're essentially eliminating ammonia. That's right. But we're not directly eliminating ammonia. We have to do some modifications first. So for example, you can take this primary amine and go through this whole process, and you can get styrene, which is a useful monomer in the formation of, styrene cups and other things like that. Okay? And it's a pretty good elimination technique. It does have some problems. Can anybody tell me what the problems might be? One, silver is not cheap, right? It's a precious metal. It's not the most expensive precious metal, but it's kind of costly. So you're taking a precious metal like silver and you're getting a cheap commodity like styrene. Not a very practical. If you actually did this process to make styrene, your Starbucks cups would cost more than the coffee. Okay? Yeah. So the way that this happens is when you have an excess of iodomethane, the primary amine becomes a quaternary ammonium salt. Remember, amines will react with alkyl halides, and they do that until they form quaternary ammonium salts. Because the primary amine is more reactive than ammonia, and then the secondary amine is more reactive than the primary amine, which is more reactive than the quaternary ammonium salt that you get. And then when you add silver oxide, notice what happens. What's our counter ion? We've got a quaternary ammonium salt, but what's the counter ion now? N plus, what's the counter ion? OH minus. Is that what you would have expected just from the treatment of the primary amine with alkyl halide? So let's take this primary amine and let's work through it. So what happens, Matthew?
Okay, lone pairs attack carbon, which then puts up the ion.
Okay, and we make a new
Carbon-nitrogen.
carbon-nitrogen bond. Right? Ultimately, you make HI, which gets absorbed by base. You have to have a little extra base around for this to happen. Usually this is done in like sodium hydroxide. So now what happens? It reacts again with the iodomethane in the same reaction. And now what happens? It reacts again. I'm not going to show the mechanism over and over again. And we get the quaternary ammonium salt. What's the counter ion at this point? Iodide. That's right. Is iodide a good base? No, not at all. So what's the purpose of the silver oxide? What happens if you take silver ion and you put it in the presence of a halogen? Think of, it does. It precipitates out. You're thinking back to your Gen Chem spot test, right? And so silver oxide can really be thought of as a solution of silver hydroxide. It doesn't really exist that way, okay? But you can think of it. And so what happens is the iodide reacts, you get silver iodide, which is a solid precipitate, and you exchange the anion. This whole process, surprisingly enough, is called anion exchange. Huh? Very creative. Or anion metathesis. But nonetheless, it is anion exchange. You're exchanging one anion for another, and you're using solubility rules to do it. So your Gen Chem comes back into play. And so now we have a good base around that can actually do the elimination. And so what happens is the hydroxide now will attack one of the beta hydrogens and give us our products. What's and it goes through an E2 elimination. But what's kind of unique about the product distribution? What's kind of strange? It does not follow Zaitsev's rule. It follows the Hoffman rule, surprisingly enough, right? Or as Sarah would say, that's creative, right? So I want you to explain to me right now why the major product is not a Zaitsev alkene. Because I thought that the more substituted alkene was the more stable. Is that statement not true here? The more substituted alkene still is the more stable. So why am I going through a reaction here that gives me the least substituted alkene and the least stable alkene product? What's the reason? Nope, doesn't have anything to do with the fact that I'm heating it. Ah.
Good job, man.
Explain it to me, though. That's just a statement. Now explain the statement. But why? Explain to me why on relative grounds. It can attack either of the two beta carbons, correct? That's a true statement, but not an explanation. Right? So if we look at the molecule, right, we've got N, and we've got a hydrogen. Let's see, where's the methyl group? Here. Okay, so we've got hydrogen here, and we've got hydrogen here. Now, the hydroxide could attack at this beta carbon and give me the more substituted alkene, which is the more stable, plus trimethylamine leaves as the leaving group, okay, and water, of course. Or hydroxide could come in here and do the same thing, which we'll call pathway 2. And you get the trimethylamine and the water leaving. What's different about those two pathways? Is it just the methyl group? Because if it was just the methyl group, you would predict that it would be a Zaitsev product. Keep going down that rabbit hole. So when my base is coming in here, it has to interact with this group, right? And is this small or large? It's fairly large. So it has to cram in between two large things. Here, the hydroxide just has to deal with the one large thing, not two. So it's not being crammed in between two large. And so you end up with the least substituted alkene. And that actually turns out to be pretty useful. If you want A to be the product that you want to make, you can't use an alcohol and do a dehydration. You'll get the Zaitsev product. But I can use the amine and do the Hoffman elimination procedure and get the least substituted alkene. And so that turns out to be a fairly useful reaction because it gives us the least substituted alkene. Okay? So I'm going to show you a real example of when I used this reaction when I was a graduate student. So I started off with xylene, paraxylene, which is just an aromatic ring with two methyl groups in the 1,4 position. And I treated it with N-bromosuccinimide, and I did free radical chemistry. What was my product? And replace it with what? Bromine. It's free radical halogenation of the benzyl group, right? So I took off one of the hydrogens in a chain mechanism. I mean, I'm oversimplifying here. Took off one of the hydrogens and replaced it with bromine, and I got a benzyl bromide. Okay? Now I've got a good leaving group, right? Now I took that and I treated it with trimethylamine, which is a gas. And it stinks. And I did not wear my Sunday best, believe me, because all day I smelled like dead fish. But trimethylamine reacted with the alkyl halide in what kind of reaction? In an SN2 reaction, it gave me a quaternary ammonium salt with the bromide as the counterion. Okay? And then I took that and I treated it with silver oxide and water, and I did what? What did that do for me? Changes the counterion from bromide to hydroxide. That's right. But in the process, I did the Hofmann elimination. What's kind of strange about that Hofmann elimination? That's right. This is called an extended Hofmann elimination. So let's draw it here. And I'll just draw in one of the hydrogens like this. And so once I generated this, even a little bit of heat, this reacted with this hydrogen. And I got this nice little molecule. Do you think that's very stable? Why not? I took an aromatic ring and I made it non-aromatic. That's exactly right. And a neat little reaction happens when you generate that. Huh? I made a popsicle? A bicycle? What are you talking about? And I got this thing called 2,2-paracyclophane. That molecule, at the time, that little molecule was more expensive than gold. Okay, it's a little simple molecule. It's actually used in the polymer industry. It's used to make coatings on very, very expensive electronic devices. Usually they end up in outer space or in the deep ocean. It's called parylene, polyparylene. Okay, but that's the well, not the monomer. That's the dimer to it. And so this molecule can also polymerize into a polymer. But we used a extended Hofmann elimination to get this, which then dimerizes to give me the 2,2-paracyclophane at about 10% yield. It's not a very good yielding reaction. But when you're making something that's as expensive as gold, you can live with a low yield reaction. Okay? Huh? No, they got cheaper ways to make it now, and so I've got a whole pound of it in my lab now. But yeah, all that work. No, actually, I bought it from a company that sells it to companies like NASA and other things to coat very expensive stuff. Can anybody tell me what's kind of interesting about 2,2-paracyclophane?
That bond is really weird.
What bond is really weird?
The bond connected. Yeah.
These two aromatic rings are actually on top of one another, connected by, they're actually sandwiched. And they're so close together that the aromatic rings actually pucker a little bit. They're no longer perfectly planar. And so it turns out that the two aromatic rings are so close to one another that it behaves as if it's one aromatic system. This ring can actually talk to this ring electronically. So when I do something to this ring, the other ring knows that it happened. And you can do chemistry that's kind of cool and neat with it. But we would add a group to it. If you add one single group to 2,2-paracyclophane, it becomes chiral. And that's why I was interested in it. So we were interested in the chiral molecules that don't contain chiral centers. And 2,2-paracyclophane is a good example of that. Okay? So we were going through these quaternary ammonium salts. I did not get to it from a primary amine. I used a tertiary amine, trimethylamine, to react with the benzyl bromide that I generated to make the molecule. Okay?
That reaction mechanism is not practical anymore, right?
To make the 2,2-paracyclophane?
Yeah.
Yeah, no, that's not a very practical way of making it. I mean, a high-yielding way. It's not. It's not. I don't remember how they'd go about doing it now, but there's a more efficient way to derive it. But at the time, I mean, this was a known procedure, and I was a graduate student. I didn't want to spend any more time in grad school than I had to, so I just followed a procedure to get me what I needed. Yeah. And so that took about 2 days. The worst part was working with the trimethylamine, which is, like I said, a gas. Amines will also react with nitrous acid. Okay? Nitrous acid you get when you take sodium nitrite and you react it with HCl, you get nitrous acid, okay, plus sodium chloride. Does anybody know what nitrites are used in?
No.
It is a preservative.
Preservative for wine, right?
That's sulfites.
Sulfites, okay.
But it is a preservative. Can anybody tell me
For meat?
for meat? That's right. So those flavorful canned meats that a lot of people like actually contain nitrites, and they're good preservatives, but they will react with HCl to make nitrous acid. If I eat some of this meat, where would they come into contact with hydrochloric acid? In the stomach. That's right. And so if you've ever read on any of those nice canned meats, they say they contain nitrites. The reason they tell you that is because nitrites are a suspected carcinogen. Okay? So, and it's because the sodium nitrite gets into contact with my stomach acid and it makes nitrous acid. Now, the mechanism for the formation of nitrous acid, pretty straightforward. It's just the nitrite functioning as a base on the strong acid to form the nitrous acid. But the nitrous acid will continue to react. And so this OH gets protonated by the HCl. Now I've got what looks like a good leaving group, right? And this can then leave. And I get what's known as the nitrosonium ion, which is a very potent electrophile. It will react with all kinds of nucleophiles, okay? It's pretty potent. It's not NO2+, it's NO+. It's a very potent electrophile. And as you can imagine, it will react with just about anything that it comes into contact with, particularly amines, okay? And so, for example, if I take a primary amine and I treat it with nitrous acid, which is just depicted as sodium nitrite and HCl, okay, what falls out of solution is called a diazonium salt. So what have I done? I've converted the amine into N2+. Okay? So what's happening is the nitrosonium ion reacts with the primary amine, and I replace those two hydrogens with another nitrogen, triple bond. So there's a positive charge on this. This reaction occurs very, very readily. It's one of the easiest reactions to do. You take HCl, sodium nitrite, you put in a primary amine, and out falls these diazonium salts. These diazonium salts have a nasty habit of being explosive. Can anybody tell me why they might be explosive?
Is it not because of the, no, I'm not going to say it.
What does it look like if you ignore the R side of it? Looks like nitrogen, right? Nitrogen gas. And if I release a bunch of gas at once, what do we call that?
Explosion.
That's an explosion, right? That's exactly what it is, right? And so these diazonium salts can be explosive, but they can also be very useful. So for example, if you take aniline and sodium nitrite and HCl, you get this aryl diazonium salt, which falls out of solution. And these are actually used to make dyes. So you can make diazonium dyes. You all are wearing diazo dyes right now, probably. Yellows, greens. I don't know. You got any color? Yeah, a little color. I don't know about brown. But they're useful materials. And this is a reaction called diazotization. You're taking an amine and converting it into a diazo compound. Okay? And again, it is a very useful reaction. The mechanism is pretty straightforward. Like I said, the nitrosonium ion is a pretty potent electrophile. The primary amine reacts, okay, and you get this molecule. You've just formed the nitrogen-nitrogen bond. Chloride then comes in and abstracts the hydrogen from that one nitrogen group, and you get what's known as an N-nitrosamine. Those are carcinogenic. Nitrosamines are carcinogenic, and that's why eating a lot of canned meats isn't really healthy for you, other than the cholesterol issues and those kinds of things, okay? There's many reasons not to eat those good things. But nonetheless, these are the carcinogens. But these will continue to react. with HCl. The nitrosamine will react with HCl and ultimately give me the diazonium salt plus water. I don't really care at this point that you remember all the steps in that mechanism. What I want you to know is that if I take sodium nitrite HCl and a primary amine, I'm going to get a diazo compound. That's what I want you to know. Because I'm more interested in what you do with those diazo compounds than you are in how the diazo compound was formed itself. That's where the interesting stuff is, in my opinion. Okay? A secondary amine will not form a diazo compound. It stops at an N-nitrosamine, okay? Because we don't have that other hydrogen on that nitrogen to continue the elimination of water. Okay, and so these secondary amines are really bad because they stay as nitrosamines. And they, as I mentioned, they are carcinogenic. Okay? So a primary amine reacts to give a diazo, and a secondary amine reacts to give a N-nitrosamine. And an N-nitrosamine is an intermediate for a primary amine, but it's not the final product. Okay? Now, the cool thing about these diazo salts that we can make from like aniline is that we can actually use it to replace the nitrogen with another nucleophile. So, for example, if I take the diazo salt here that we got from aniline and I boil it up in water, I get phenol. That's a useful functional group. Phenol is available in a lot of medicinal materials, other compounds and other materials, and so it's a pretty convenient reaction. Anybody want to take a stab at the mechanism? It does. Got any idea what it does? I mean, if we could just wave our magic wand, it looks like it's just removing the nitrogen and replacing it with an oxygen, right? But that's not really what's just happening. What's happening? What's happening is the water attacks the carbon bearing that nitrogen.
Like an intermediate or something like that?
And you get an intermediate, which then eliminates the nitrogen, and you end up with a phenol. So it's like an addition elimination mechanism. And we'll be talking more about that in the next chapter, tomorrow actually. Okay? But we can use other nucleophiles. So for example, I can take that diazo salt and I can react it with copper chloride, and I can make aryl chlorides. How else can we make aryl chlorides? FeCl3 and what else? FeCl3 by itself won't do it. And what? And chlorine. Yeah, we can do electrophilic aromatic substitution, right? But we got to work with chlorine gas there. Am I having to work with chlorine gas here? No. So it's a pretty convenient way to do this in the laboratory. I can also make aryl bromides by taking the diazo salt, reacting it with copper bromide, and getting the aryl bromide. These reactions are known as the Sandmeyer reaction. When you take a diazo salt and you convert it into an alkyl or an aryl halide, this is known as the Sandmeyer reaction. And you need to know that reaction by name. Okay? There is. I won't deny it. It's a good carrot. But it's really important for this reaction 3. Can anybody tell me why this is so important? Fluorine. I showed you no way to make aryl fluorides, right? I said we can make aryl chlorides, we can make aryl bromides. I think I even showed you a way and briefly mentioned it that you can make aryl iodides. But aryl fluorides, I said if you take benzene ring and fluorine, it goes boom, right? But we can do it here. All we need is a source of fluoride, and we use HBF4, okay? And so that is a good source of fluoride. And it will work because I don't have F2 around, okay? So it works pretty well. We can make aryl fluorides. And we can also make aryl iodides really convenient as well if we use sodium or potassium iodide. So The Sandmeyer reactions work pretty well. We largely lump them into this Sandmeyer category, although these last two are technically not Sandmeyer because we're not using copper, but they do basically the same thing. Do you have a question about that, Harrison?
Yeah, what would you use our fluoride for?
It turns out that putting fluorine on aromatic rings of molecules makes drugs better. So a lot of drugs that you take today are expensive because they actually contain fluorine. Fluorine is or organofluorines are actually privileged functional groups in medicinal chemistry. And so a lot of times if they find a drug that works pretty well but not well enough, they'll start putting fluorines on the aromatic ring. And it almost always improves the pharmacological activity of the drug. Not always, but putting fluorine on is a big thing in the pharmaceutical industry. Why does it help? There are electronic reasons, so electronegativity is part of it. But what do we know about fluorine? What will it do that hydrogen won't on a carbon? It will form hydrogen bonds. Remember, the carbon-hydrogen bond doesn't really form hydrogen bonds. I know Dr. Wallace says it does, but that would be bad. Okay, so, almost. But the fluoride will form hydrogen bonds, and we know that sometimes that's important to have an aromatic ring that can form a hydrogen bond but not have any other reactivity associated with it. So these fluorines, and there's many other reasons, but this is one of the reasons why. So being able to put a fluorine on an aromatic ring is kind of important. Okay? And this is actually the most convenient way of putting an iodine on an aromatic ring is to actually use these diazo salts. So with this in mind, I want you to, on a piece of paper, I want you to figure out how to take benzene and convert it into 1,3,5-tribromobenzene using any chemistry that you know right now. Will I get me something to drink here? What do you think the problem is, Sarah? If I look at that product, why can't I just put bromines on directly? All right. Bromine is an ortho-para-director, but it's a deactivator, right? Okay. So let's assume we can put all three on. They're not going to go in that order, right? Because they're how with respect to one another. They're all meta. Right? So,
what if you had a bunch of meta-directed groups in place of boron bromine?
Okay, so tell me what you want to do. All right, let's put a nitro group on it. HNO3, H2SO4. You put a nitro group on it. Now what's going to happen?
It's slightly deactivating.
Is it slightly deactivating?
It's a
Strongly deactivating. So do you think I'm going to be able to put another group on that's also deactivating and then another group on that's deactivating? No, really. Sure. So what can I convert this to that would be an ortho-para-director? Say a strong one. What can I convert nitrobenzene into that would be an ortho-para-director? Yeah, so how do I do that? Okay, iron and HCl. That works. We just made, assuming appropriate workup, we've just made aniline. Gabby just mentioned to us that that is an ortho-para-director and it's a strong one, right? So now Nate comes along And he treats this with an excess of bromine, some iron filings from a nail he's got in his pocket for whatever reason.
Sketch.
Hey, you never know what part of the neighborhood you're going to end up in, right?
I mean, it's mental, so it can just drop out the tip and say no.
Nailed it. So where are the bromines going to go?
We'll still be
Ortho and para to what? To the NH2, right? And it's a strong activator, so that's going to happen. Notice I have my bromines now in the position that I want them in, right? What's the problem? Got to get rid of the NH2. Essentially, that's what I'm going to do. What can we do to the NH2? I can diazotize it, right? I can convert it into a diazo. So now what do I have to do? How do I erase it?
Now replace it with hydrogen.
I got to replace it with hydrogen. Hydrogen or hydride?
That'd be a hot NaH, right?
Hmm?
Would it be?
Well, you're having fun there, aren't you? I got to replace it with a hydride. You guys know of really two hydride sources. Well, you actually know three, but the two that you really know of are LAH and sodium borohydride, sodium cyanoborohydride, those things, right? Those won't work here. There's another hydride reagent, okay? H3PO2, hypophosphorus acid. It actually contains a hydrogen phosphorus bond, and it's a pretty decent reducing agent. H3PO2 will reduce that diazo off and replace it with a hydrogen.
So why can't the other ones do that?
They actually reduce the nitrogen triple bond. Hypophosphorus acid. I like to call it H3PO2. So basically, over those, how many steps? 5 steps, we made 1,3,5-tribromobenzene. And it turns out that's the way you got to make it if you start with benzene. Because I can't just brominate. If I was to brominate, the first bromine goes on, and it's an ortho-para director. So I'm either going to get 1,4 or 1,2 relationship, and then if I was able to put on a third one, it wouldn't be all bromines meta to one another, would it? So we can do that through this type of chemistry pretty readily.
Wouldn't it be more, and that's why it says that you hydrogen gas and flavor.
Which?
That one?
Oh, yeah, you could, but we chose iron and HCl.
Isn't one of that more practical?
This is more practical, or more cost-effective, I should say. But you could use catalytic hydrogenation. That's just what they chose to use. What would I count correct on the exam? Either. Yeah, I'd count either correct. No problem. Now, these diazo compounds are useful for more than just Sandmeyer-type chemistry. They're actually useful because they will react with other aromatic rings to make azo compounds. Okay, so for example, if I take a diazo salt, and I react it with, let's say, a phenol, Y is OH, it will actually couple the nitrogen to the aromatic ring, basically through electrophilic aromatic substitution. The mechanism is the same. The electrophile is just the diazo compound. But the mechanism is the same. The nice thing about these compounds is that I have a lot of conjugation here, and a lot of conjugation here. And when I have things that are highly conjugated, they become colored. Remember, beta-carotene contains a lot of conjugated double bonds, and it's the color of the carrots, right? Speaking of which, I'll get another one here. Yeah, Harrison, good job. Now, if you look at the example below, this yellow compound called butter yellow was made. And if you know anything about margarine isn't yellow when they make it from vegetable oil. It's colorless. But people don't like spreading colorless stuff on their toast in the morning. They think it should look yellow, like butter. So what they did was add an artificial dye called butter yellow to the margarine that gave it the yellow color. Okay? Most azo compounds are toxic. Many of them are carcinogenic. So spreading that healthy margarine on your, it was in small concentrations. I mean, was it going to? It's better than lard. Yeah. That's over long periods of time. I don't know how, well, I guess you could be eating a lot of butter. I don't know. Yeah. But it is no longer used to color margarine. But nonetheless, you can make a lot of different dyes. Depending on what this group is, and if you add other groups to this ring, you can change the colors. You can go from yellow to blue to red to purple. You can go basically throughout the rainbow by changing how the electronic structure of the diazo compound is. And so these have been incorporated into dyes, which then are used to color your clothing and other things, your Easter eggs, whatever the case may be. And but it's all made through this chemistry that you're learning about in sophomore organic chemistry. Okay. One day you might have a job. I'm going to post this to YouTube tomorrow.